Hey everyone, we're just about there, 1 o'clock. Okay, yeah, it's 1. All right, so I was looking at the calendar, and today we are going to cover 4.1, but today is the 15th, so we are still behind. I mean, I wasn't sure how far we would get in the class with all the delays we had, but you know, this is where we are. Let's see if we can get through 4.1. Maybe we can get through 4.2 today. It just depends on how 4.1 goes. But that's our task today, is to finish 4.1. So last class we were talking about looking at local maximums and local minimums, and then also global maximums and global minimums, right? And I had shown you, you know, visually what those things look like. So I had shown this to you, and we come to our first theorem. Okay, so this is an important theorem. It's called the extreme value theorem. So a theorem is just a mathematical statement that is true. All right, so this says, and we have to read this carefully. It says, if f, man, what is going on with my damn thing today? I'm having a lot of issues here. Give me a moment. Let me see if this will work. Let me try this again. Okay, let's see if this works now. There we go. Okay, so the theorem says if f is a continuous function. All right, so that in itself means that if we're looking at a function that you can basically draw without picking up your pencil, and we're looking at that continuous function on a closed interval. Now that's also important. It means that the graph is going to start somewhere at a point. It's draw it without picking up your pencil, and it's going to stop somewhere. So if we have those two conditions, okay, that it's continuous and we are defined on a closed interval, then the conclusion is that f must attain both an absolute maximum value and an absolute minimum value on that interval. So it's saying that if you draw a graph from one point to another and you can't pick up your pencil, then you're guaranteed to have a highest point and a lowest point. There's no way to do it without having some absolute max and absolute min. Does it make sense? I mean, does that make sense visually? If you connect these two dots with a curve, you're going to have a highest and a lowest point somewhere. Yeah. Okay, so here are some specific examples. So here's an example of, oops, yeah. There we go. There's an example of a graph where it's kind of hard to see this. It goes up and it curves down a little bit. So do you see that this is a continuous function that has an absolute maximum here and an absolute minimum here? Right? That's pretty straightforward. Yes. Here's another example. Okay, of another graph. Let me take the other one off of there. Let me get that out of there. So here's another example where we start here, we draw it, and it ends here, and you can see we have a global maximum here and a global minimum here. Another example. How about a straight line connecting 2 points? Well, the endpoints would be where we have the absolute or global max and the global min, right? In this case. 1, 1. Oh, okay. What about this? What happened here? We start to draw from here, and then this looks like with the dotted line. Do y'all see I'm kind of representing a vertical asymptote here?
It's not a function.
I'm sorry?
It's not a function.
Well, it's still a function. It is a function because it passes the vertical line test, but is it continuous?
No.
It's not continuous, which means that the theorem does not apply. And so if we're looking for absolute max and mins, we would basically say we can't use the extreme value theorem. The extreme value theorem does not guarantee us an absolute max and min unless we have continuous on a closed interval. So that's just a final example to just illustrate how it's important for us to make sure that the two conditions are met, or else we can't use the theorem, okay? All right, so now we move on to the next theorem, which says that a function, or it says if a function f has a local maximum. Remember, local meant that you're not necessarily the highest point in the whole graph, but locally you are. If a function has a local maximum or a local minimum at some point C, and so there are two conditions that have to be met here. If we have a local max or min, and the derivative exists, the conclusion is that the derivative must be 0. Okay, so this theorem says if we have a function and it has a local maximum or minimum, if it has one, and when you go to that point, the derivative exists, then we can be guaranteed that the derivative is 0. Now, this theorem is actually confusing because you can use it incorrectly. So we want to be careful with what it's actually saying, and that's what I put here. This theorem is important. It states that if our function has a local max or min and the derivative exists, then the derivative must be equal to 0 there. It does not say, okay, it does not say that if the derivative is 0, then we are sure to have a maximum or minimum. So I'm going to try and illustrate what I mean by this. And I may have used this before in this class. If I write this down, if you live in Texas, right, then you live in the United States. We all agree with that? If you're from Texas, you live in the United States.
Yes.
This is not the same as you cannot reverse this and have it still be true, right? If you live in the United States, then you do not have to live in Texas, right? So you cannot just arbitrarily switch the order of a statement and it stay the same. So this theorem says if we have a max or min, so if you're looking at a local max or min, and the derivative exists, then you're guaranteed the derivative is 0. It is not saying that if the derivative is 0, then you have a max or min. Is that clear? Because I don't want you to walk away from this saying, oh, what I learned today is that if the derivative is 0 somewhere, then I have to have a max or min. No, that's not what it says. Okay. However, even though that's not necessarily, or doesn't necessarily seem like this will be useful, we're going to have another theorem here in a second that will clarify this and will be very useful. So I'd like to give you an example of this theorem right here. It's actually called Fermat's theorem. Here's an example of a function where the theorem actually does apply. So do y'all see that we have a, excuse me, we have a local maximum here and a local minimum here? Do y'all see those two red dots, a local max and local min? And do you see that the slope of the tangent line, which I'm doing with that purple, that represents the derivative, right? Do y'all see that the derivative is 0 there because it's flat, right? So we had a local max and the derivative there is 0. We had a local min and the derivative there is 0. Let me show you an example now of where Fermat's theorem does not work. Okay, is that point a local maximum? Is it the highest point around here? It is, right? It is. It is a local maximum. However, the derivative there does not exist. Why doesn't the derivative exist? Do y'all remember?
Yeah, you had like a whole bunch of different things.
There were three ways a derivative can't exist. It can't exist at corners or cusps. This is a corner. Can't exist anytime you have a jump or a break in the graph. And it can't exist anytime you have a vertical tangent line. Those were the three from way back when we were talking about derivatives. So even though this is a local maximum, the derivative doesn't exist. And that means the derivative does not have to be 0. That's, again, the theorem says if you have a local max and the derivative exists, which it doesn't, then the derivative must be 0. So this is just illustrating, again, you have to be careful with the theorem. You can still have a local max and not have the derivative be 0. Here's another example where we have where it fails. Is this point a local max or min? Is it the highest point or lowest point? Is it the top
Straight
of the,
line.
of the valley?
Available.
No, right? It's not. Is the derivative 0 there? Is the slope of the tangent line 0? It is. So just because the derivative is 0, that again does not mean that you have to have a local max or min. Okay, I understand when you first see this, this can be somewhat confusing. So let's just keep moving, all right? We now have a definition, and this is a very important definition, all right? It's the definition of what is called a critical number, or the critical numbers of a function. A critical number of a function, f, is some number c in the domain such that one of two things is true. Either 1, the derivative is 0 there, or 2, the derivative doesn't exist. So if we have a function and we can find the places where the derivative is 0 or where the derivative doesn't exist, then we have found what are called the critical numbers of the function. All right? Those two conditions are not conditions. If one of those two things is true at some value, then we have found what is referred to as the critical number. Now, with that definition in mind, we have a new version of Vermont's theorem, and this is the one that is going to help us finally be able to solve some of these problems in this section. If f has a local maximum or minimum at some point c, then c must be a critical number. So if you have a maximum or minimum at some point, then that point must be a critical number. That's a very important theorem. So here's how we're going to use it. All right. Here's how we're going to put all this together into one final sort of like, what the hell are we doing in this section? Our goal is to try and find the absolute max and absolute minimum values of a function on a closed interval. So back to the very first drawing I gave you today, we have a point, the function starts and stops. We want to be able to find anywhere where we have maxes and mins, right? All of those points are going to be either local maximums or local minimums. The endpoints also could be max and mins, and we want to be able to find the globals. So that, do you all agree, is the lowest point on the graph? And that right there is the highest? So global minimum, global max? Yes? So we want to be able to do any function. What, Danielle?
Oh, they kind of look like they're at the same, like,
Yeah.
height. So sorry.
Yeah, so that one's a little lower. Sorry, I know it was a little hard to see that, but okay.
Thank you.
All right, so if you haven't really been following what I'm saying up to this point, then this is really the main idea of today is this 4.1.11. All right, this is the big deal right here. This is what we're going to be using. So this, what I'm about to show you, is called the closed interval method. And it is a method that we use to find the absolute maximum and minimum values of a function on a closed interval.
Hey, Professor.
Yes.
I just have a quick question. As you said, like when we have a local minimum or maximum, then our derivative should be 0.
Could
Right.
be 0.
Okay,
Could be. Doesn't have to be.
right. So like, does that mean it's also like that derivative is also a critical number, or like critical number is separate than a derivative?
A critical number is any value that when you plug it into the derivative, you get 0 or the derivative does not exist.
Okay.
That's what a critical number is.
Thank you, sir.
Okay, this will all become more clear when we do examples, I think. All right. So let me tell you what the closed interval method is. You need to know this method. You need to know how to execute it. And it's only 3 steps, okay? So it's not like this big old long drawn out process, but there's a lot of work that's going to go into each of these 3 steps. All right, so to find the absolute maximum minimum values of a continuous function on a closed interval, continuous function, we must have a continuous function on a closed interval. In order for us to do that, number 1, first step, we find the critical numbers of the function. Okay, what does that mean? I want to find where the derivative is 0, and I want to find where the derivative does not exist. DNE doesn't exist. That's what the critical numbers are. Once I find what my critical numbers are, I will evaluate the function at those critical numbers. So I'll take whatever answers I get here and I'll plug them into the original function and I'll see what answers I get. The next step is to evaluate the function at the endpoints of the interval. So I'll take the 2 endpoints and I'll plug those into the function. And then once I've done that, I will just compare everything I've got. I'll compare all my answers. And the biggest answer I get is my global maximum or absolute maximum. And the smallest number I get will be my global or absolute minimum. And that's it. That's what we do. All right. So I'm going to follow these steps. Let's start. Let's do a problem. And like I said before, I think this will all start coming together as we do examples. All right. So I want us to find the absolute max, and I want us to find the absolute minimum of the function f of x. We're going to start out very simple, x squared minus 4x on the interval, let's go -1 to 3. So before we actually do this, I'm going to graph this for us, okay? It was x squared minus 4x. And then we are on the interval -1. What did I say, -1 to what? -1 to what?
Listening. What was it? No.
Is it a -1 to 3?
3. There we go. So if I take this graph, x squared minus 4x, and I only graph it between x is -1 to +3, we are going to try and find what the highest and lowest points of this graph are. Okay, and I think they're clear from the picture that this should be our max, right? That should be our absolute max. And this point down here should be our absolute minimum. Do y'all agree? Okay, but let's act like we don't have the picture, right? And let's go do it with calculus. We will now find where these 2 points occur. Any questions?
No.
Okay, so here we go. So I'm going to use the closed interval method. Now, the reason I'm using the closed interval method is because first, my function is continuous. Can somebody tell me why you know it's continuous?
It's a polynomial function.
It's a polynomial function, right? All polynomial functions are continuous. How do you know that? Because we discussed that way back when we were talking about what makes functions continuous, which was many sections ago. So all polynomial functions are continuous, so we're happy about that. And then the next condition you need is you need a closed interval. And we have that, right? If we have a continuous function on a closed interval, then we can use the closed interval method. So the first step to the closed interval method is I'm going to find the critical numbers. And what that means to me is that I need to figure out where the derivative is 0, and I need to figure out where the derivative does not exist. So let's start with the first thing. We're going to need the derivative, aren't we? Like if we're going to figure out where it's 0 and where it doesn't exist, we need the derivative. So I may as well take the derivative right now. The derivative of this function is just 2x minus 4. That's just the good old fashioned power rule. 2 comes out, right? Derivative of negative 4x is negative 4, and we're done. Now let's check the two things. First, where's the derivative 0? Well, that just means I need to take the derivative and set it equal to 0. And that's a nice little linear equation, right? We can just move the 4 over to the other side, adding it and divide by 2, and we get x is 2. So far, we have one critical number. It is 2. Now I need to ask myself, where does the derivative not exist? Well, look at your derivative. 2x minus 4. Is there any number that you can't plug in? Like, are you ever going to get like division by 0? Are you ever going to be trying to take square roots of negative numbers? Are there any domain issues with the derivative?
Yes, because you're on the closed interval.
Well, there are certain numbers I can't plug in because of the closed interval, but I'm saying within this interval, is there anything in here that I could possibly plug in here where I'd be like, oh, that's undefined?
No.
No, right? Because you don't have division, right? You don't have like x in the denominator where maybe you get division by 0. You don't have like square roots. You don't have like a tangent or cosecant or secant. You know, sometimes trig functions are undefined. So this is a very, very nice function. We can plug any number between -1 and 3 into this, and it'll just spit out a number, right? So there's no problems with it, the derivative ever not existing. Do you all see that? The derivative is well defined. So we only have one critical number. So according to the the closed interval method, I'm supposed to find the critical numbers and then evaluate f at those critical numbers. So let me do that step now. I only have one critical number. So I'm now going to evaluate f at x equals 2. In other words, what I'm going to do is plug 2 into the original function,
Oh,
And so, go ahead.
I wasn't able to understand. So it's okay that we don't have a does not exist, and with this one is does not. We can cross out does not exist because of why? There isn't a number that we can put in there that's going to give us something undefined.
That's right. There, if you look at 2x minus 4, you give me any number between -1 and 3, anything you want. I don't care what it is. I'll always be able to multiply times 2 and subtract 4. Let me just show you, what if, just for the sake of trying to be clear here, what if our derivative was 2 over x plus minus 4? Okay. Let's just say that's what it was. Okay. Then I would have a problem, wouldn't I? I'd have a problem if x was 0. If x was 0, I'd have division by 0. And 0 is in here, isn't it? -1 to 3, 0 is in there. So I would have another critical number. I would say the derivative does not exist at x equals 0, but that would become a critical number then. Okay? But that's not what we have, because we have a very nice little linear function.
A nice little cute thing, yeah, going. Okay, thank you.
Okay, so right now we found a critical number of 2. We plugged into the function, we got -4. Okay, we are done with the first step. The next step for the closed interval method is to evaluate the function at the endpoints of the interval. So that just means for step 2, I need to evaluate the original function at the 2 endpoints. So I need to figure out what's f of -1, and I have to figure out what's f of 3. So let's plug -1 into the original function. You should get 1 plus 4 here, and this should be 5. And then if you plug in 3 and square it and subtract 4 times 3, This should give you 9, take away 12, which gives you -3. Is that right? 9, take away 12, yeah. Any questions on that? Step 3, compare the answers from the previous two parts. The largest answer we get is the absolute max, and the smallest is the absolute min, and we're done. So when I look at this, the largest value I see is 5. That means that this is our absolute max. And if you want, you can write it as a point. It's the point -1, 5, right? When we plug -1 into the function, it spits out 5. And since 5 was the largest of these answers, that's guaranteed to be where we have the absolute maximum for this function.
Is that how you want us to write it to get good practice on using that? Or are we going to need
I
to do
think
that?
that you can do it either way. If someone asks you what's the absolute maximum, you would say 5. But if someone said, where did it occur? Like, where does the function have its absolute maximum? You would need to know it happened at -1. I personally like
Okay.
writing it as a point because it gives you both pieces of information, not only what it is, but where it happens. Now, the minimum
Okay.
is the -4. That's your absolute minimum, because that's the smallest number. Remember, on a number line, the way things work, here's 0. As you move that way, you get big. As you move that way, you get small. So -4 is here, -3 is here, right? That was -3, that's here, and -4 is to the left of it, so it's smaller. So just want to make sure everyone understands, this will be our absolute minimum. And if I write it as a point, it's the point to -4. Are we good? Does everybody see that that matches with what we said we were going to have here? Right? We had at, what is this value? It looks like it's about what, -1. We go up and boom, up here, that's 5. So that was the point -1, 5. And then this point right here, it's let's see, 2 on the X, and this is -4. So there we go. That matches exactly with what we got, right? Now, theoretically, we can do this for any continuous function on a closed interval. It doesn't have to be a simple parabola. It can be any function, all right? So y'all ready to do another one? You ready for this? Here we go. What do you think is going to get more complicated now?
The problems themselves. I was thinking like,
You're
you
gonna
know, like how you said, oh, this is
This-
all like cute, nice little linear thing. Like, you know, is there going to be a problem when we're having like, you know, chain rule having to get involved in this whole guy?
Yeah, I mean, that's
Or
really
anything?
where we're headed with this. It's like, okay, well, you know, that was a simple function. The derivative was simple. Setting the derivative equal to 0 was simple. What if it's more complicated, right? So why don't we do the same thing? I want us to find the absolute max and the absolute minimum of the function f of x equals, I'm going to make this up. So since I'm making this up, we're probably going to get some weird answers. X cubed minus 4x squared plus 2x minus 3. And I want this on the interval. Let's go -2 to 5. No, we'll go with it. Okay.
Are we ever going to be asked to find local maximums, and like how would we find, like how would we tell if it's a maximum or minimum, like a local?
Yeah, good question. The question is, will we ever be asked to find local maximums and minimums? And how do we do it, right? Well, that's actually not the next section, but the section after that. So right now we're focusing on continuous functions on closed intervals. Later, we want to say, what if you're just trying to find local maximums and minimums of the function on their entire domain, and you no longer are closing it off? That's a different method. It's much more difficult. There's a lot more involved. Okay, but we have to start with the baby steps. This is closed interval method. It's pretty straightforward. You always want to use closed interval method when you can. If you have to do the other method that we're going to learn, then, well, you have to do it. But if we can somehow get it on a closed interval, we want to do this method. All right, you ready? Step one. Well, step one is this a continuous function? Yes, it's a polynomial. Is this a closed interval? Yes, right? So we've got the closed interval method. So closed interval method.
You're gonna show us one where where we can just stop, right? Where it's like, oh, this is not, or is it just like
I
obvious?
wouldn't give you a function that's not continuous and then ask you for the max and mins. I mean, it's just, I mean, could I? Yes, but I'm not trying to trick you. I want to make sure you can do this, right? Okay, so here we go. So we've got this first step, critical numbers, right? Critical numbers. So we find the critical numbers. What we need to do is figure out where the derivative is 0. And we need to figure out where the derivative does not exist. All right, so we need the derivative. Let's take the derivative. Derivative of this is 3x squared minus 8x plus 2. We all agree with that?
Yes.
Okay, now let's figure out where it's 0. Where is the derivative 0? Well, that means we have to set 3x squared minus 8x plus 2 equal to 0. So that equation is not as easy as the previous problem, is it? Right, the previous problem was a nice little linear equation. This is not. This is a quadratic equation. So how do we solve quadratic equations? You try and factor it, right? If you can factor it. If you can't factor it, then what do you use? The good old quadratic formula, right?
Yeah.
Good old quadratic formula. So this does not factor because I made up the problem. I had a feeling it wouldn't factor, but I can use the quadratic formula. So I'm going to put here QF for quadratic formula. And I'm hoping everyone remembers the quadratic formula. It says that if you have a quadratic equation, I know you're all in calculus, so you should know this formula. I'm not saying you necessarily need to know it by heart, but you should at least know it exists. Right, the solutions to any quadratic equation ax squared plus bx plus c equals 0 are given by this formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Right, that's it right there. So I'm about to use that formula. For me here, a is 3, b is -8, and c is +2. So I'm just going to plug that into this formula and see what I get. X equals -b is the first thing. So the opposite of -8 is 8, plus or minus the square root of b squared. So I take my -8 and square it. This is 64. Minus 4 times a is 3, times c is 2, all over 2 times a, but a was 3. So I get 8 plus or minus square root 64 minus, so I'm going to multiply those together. That's 24 all over 6, which equals 8 plus or minus square root of 40 over 6. And now I'm going to get my calculator out. So I'm going to take the square root of 40. I get about 6.32. I'm going to round 2 decimal places. So this is 8 plus or minus 6.32 all over 6. And now this is going to give me 2 answers. Remember, I have a plus or minus, right? Which means I have to do 2 different operations. 8 plus this, and then divide by 6, and then I have to do 8 minus this, and then divide by 6. I'm going to do that on my calculator without showing any more work. The answer when I do the plus is 2.3873. Let's just say 39. And if I do the 8 minus 6.32 divide by 6, I get 0.28. Are you all with me?
Yes.
Okay, we have two critical numbers. We have done this part. We know where the derivative is 0. Now we need to figure out where the derivative doesn't exist. So let me do that. So that was like, where's the derivative 0? Now, where does the derivative not exist? Well, does the derivative ever not exist? Look at the derivative.
It's always going to exist.
It's a, yeah.
There's no problems with this. You can always take a number and square it and subtract 8 times that number. There's no numbers I can plug in that are going to cause a problem. So this is not something we need to worry about. Now, look, there will be problems where we have to worry about it. Just this is the second example. So now that I only have these two critical numbers, what I do now is I take those values, 2.39, and I take the value of 0.28, and I plug those into the original function. The original function, which was up here. I'm going to bring it down here so I can reference it. So what I need to do here is take 2.39 cubed minus 4 times 2.39 squared plus 2 times 2.39 and then minus 3. And I need to do that on my calculator to figure out what I get. All right. Yeah, so I think it might be useful for you to have your calculators on the ready from here on out in this class. Give me a moment. I've got to change the setting on my calculator. Come on, hurry up. You can just type all that in and see what you get. Come on, hurry up. There we go. Standard. There we go. Okay, we're getting close here. I'm going to plug that number in. So when I plug in 2.39, yeah, 2.39 into that, I'm getting like negative 7.41, 742. Okay, that's what I'm getting out. And when I plug in 0.28, I'm not going to show the work here, just negative 2.73 is what I get. So all of this was step 1. Any questions? What am I going to do for step 2?
Compare the endpoints.
Plug the endpoints into the original function also, right? So I need to plug -2 and 5 into that. So I need to figure out what -2, f of -2 is and f of 5. And in an effort to save us time, I understand you would have to do this, okay? But -2 in there gives you -31, and 5 in there gives you 32. Okay. Step 3. Which is the global max? Which is the global min? So what's our global max?
5 for 32.
Yep, this is our
532.
This is our absolute max. If I were to write it as a point, it would be at the point 532. And our absolute minimum is -31, right?
-30. Yes.
Good. And that written as a point is -2, -31.
So that worked for nothing.
Well, it's not for nothing because it's not for nothing. Let's look at the graph of this, okay? Let's look at the graph of this. we look at the graph of this, it's x cubed, what was it, minus 4x squared, then what was it?
Plus 2x
minus
minus
Plus
3.
2x minus, plus 2x minus 3?
Yes.
On negative 2, 5.
Negative 2, 5. Okay, so there was the graph, right? Now I have to zoom out. Well, let me do this. I'll adjust this window. Let's make y go negative 35, and we'll go up here. We'll go to 35. Okay, so there's the graph. Can you all see this? It starts out here, it goes up, back down, back up, and it ends here. So it turns out for this particular function, right, on this interval, the global max is here and the global min is here. But it wasn't really for nothing, because what if I change the interval to like 0 to 4 instead, right? What if I went 0 to 4 instead of negative 2 to 5? Well, then my graph would go 0 to 4 like that. And now we have these points here, here, and here. This is now the min, isn't it? That's the global min, G min, and this is the G max. But I think even more important than that is that, and I had this discussion with some of you at the end of class last time, is what we're doing here is we're actually finding ways to find these local maxes and mins also. I mean, that's those two critical numbers we had actually gave us where we had locals happening, right? We go back and take this problem to the original form, negative 2 to 5. We did actually find where we have local maxes and mins. I'm going to zoom in on this. So, yeah, right, come on, do it. Right there, see that? I'm going to hover over this point. Look, do you see where that local min is? Look at the value, 2.387, comma, negative 7.417. Isn't that what we got? Didn't we have that? That was one of our critical numbers. And then look at this one right here. That's a local max right there. And look at its value, 0.279. Now we had 0.28, okay, because I rounded. But we actually have a way now of finding these local maxes and mins. Now, technically, let's just put that on pause because we're not talking about local anything right now. We're talking about global. But I think you can start to see the value of setting the derivative equal to 0 and then also figuring out where it's undefined. Okay, you ready for a new one? Everything's been kind of fun up to this point. Fun as in I've kept the functions nice. So I think I'm going to do this one a little backwards. Let's start with a graph, okay? And then I'll ask the question. So I want us to do x minus 1 over x squared minus 4.
Quotient rule.
Hold on. Yep. Let me get all this out of here. I forgot to take that all out of there. And let me see. I might want to change this. Hold on.
Doesn't that mean you have to have a hole where 2 is?
Well, it's possible to have a hole.
So something that goes off into infinity does not mean that it does not exist. It just continues forever, right? You know, it just answers my own question.
Okay, let's do that one. So x minus 1 over x squared plus 4. Think about this. Negative 6. Let's go negative 6 to positive 6. So we want to find the absolute max and min of the function x minus 1 over x squared minus plus 4 on the interval negative 6 to 6. I want to find the global max and the global min. Okay? or the absolute max and min. So same instructions. All right, so first question, is this a continuous function? Are there any numbers that you need to avoid here?
Yes.
What numbers?
-2 and 2.
Be careful, this is a
-2.
plus. This is a plus here.
Negative
Oh.
2.
So even if I plug in -2 and squared, I'm gonna get 4 plus 4.
Yeah.
So there's nothing that's gonna create 0 down here. It's impossible to get a 0 down here. Because no matter what you ever square, it's gonna be positive. You add 4, it's still gonna be positive. So you can't get 0 here, right? Now, what about 1? Can you plug 1 in?
Mm-hmm.
Yeah, you can have 0.
Yeah,
on
that
the
would be
top. That's
okay.
You just can't have 0 on the bottom, right? So this is continuous. There's no problems here. This function behaves well. And we have a closed interval. All right, so that means I'm gonna have to start going through these steps. First thing I'm gonna do, I'm gonna find the critical numbers. I need to figure out where the derivative is 0, and I need to figure out where the derivative may not exist. All right, that means I need the derivative. Well, the derivative of this is going to be x squared plus 4 minus 2x times x minus 1 over x squared plus 4 squared. Okay, so I just did quotient rule. I'll just run through it real fast. We take the derivative of the top, which is
F.
1, right? Times the bottom, which is x squared plus 4. So that's this. Minus, now the derivative of the bottom. The derivative of the bottom is 2x. There it is. Times the top, x minus 1, in parentheses. All over the bottom square. We good there? That was the raw derivative from the past, right? That's the raw derivative. But now what we have to do is figure out where this is 0. And I've been telling you about this for a while, that like the day is going to come where we have to do something with this. So now what I'm going to do is take x squared plus 4 minus 2x squared plus 2x over x squared plus 4 squared and set it equal to 0. Okay, so all I did here on this is I distributed the negative 2x through. And that gave me negative 2x squared and then plus 2x. I'm going to do some more simplification up here. Hopefully you agree that this is negative x squared plus 2x plus 4 over x squared plus 4 squared equals 0. So I just put those two together. X squared take away 2x squared is negative x squared. I had the 2x and then I had the 4. Any questions up to this point?
Nope.
Okay, very important now. Little side note here. If you ever have a fraction a over b and you're setting it equal to 0, okay? If this ever happens in your mathematical life from this point forward, if you ever have a fraction that's equal to 0, then all you ever have to do is set the numerator equal to 0. In other words, what I'm telling you is that the only way a fraction can be 0 is if the numerator is 0. If you don't believe that, then just multiply both sides by b right now. And if you do that, the b's cancel. And on the right side, 0 times b is still 0. So you wind up getting a equals 0. And you could do that for any fraction. So that's an important thing to note, because what we have here is a fraction equals 0, right? And it looks complicated. But really, at the end of the day, all I really have to look at is what makes the numerator 0. Okay, do y'all see from here to here, I'm using that property right there. That if a fraction is 0, only the numerator needs to be. And what are we looking at again?
Quadratic.
Quadratic equation, right? And so we need to go solve that. All right, we need to solve it. So it doesn't factor. So in order to save us time, I'm not going to go through the quadratic formula again, because all of you passed college algebra, so you all know how to use the quadratic formula. I'm just gonna go get us the answers. Okay, is that all right with everyone? Just gonna go get us the answers. I'm
Yeah,
not
okay.
saying that you would do this on a test, you would have to do it by hand, but I want to solve, what was it, negative x squared plus 2x
+4.
plus 4 equals 0.
Yep.
And I want the decimal answers. So negative 1.23. I'm gonna move this so I can see it, but you won't be able to see it. I'll just write down the answers for you. So our solutions here are x's, and maybe I should point out here, this is quadratic formula, right? There's a bunch of work that needs to be done here. And then you finally get to your answers. X is negative 1.23. I'm gonna say 1.24, I'm gonna round it. And X is 3.24. Two critical numbers. Y'all still with me?
Yes.
Okay. Now, one thing we need to check, and I didn't point this out. This is a mistake on my part. I didn't point this out in the previous two examples. These critical numbers that you get, you need to check that they lie within the interval that you are looking. So like negative 1.24 and 3.24, those both lie in here, don't they? So I want to check them both. If one of these answers was like 8.24, right? Then I would throw it away. I wouldn't even look at it because I'm not allowed to look past 6. Does that make sense? The
Yes,
previous
sir.
two problems, same thing happened. We had a critical number. We had two critical numbers here, negative 7.42 and negative, sorry. The critical numbers were 2.39 and 0.28. Those were both in here. So we'll just want to pay attention to that. All right, so that's this. Now I need to also ask myself, when does the derivative not exist? When does the derivative not exist? So I'm going to go back to this version of the derivative right here. Right, because we took the derivative, here was the raw derivative, we cleaned it up. I just want to look at that derivative by itself, cleaned up, right there. Can this thing ever not be defined? Is there something that would cause a problem with this derivative?
No.
No. I mean, you do need to think of maybe the denominator could be 0, right? Like what if that's 0? Then you'd have division by 0. But we already know, because of what we talked about earlier, x squared plus 4, right, can't be 0. You never can, because that would mean x squared equals -4. And we know that you can never square a number and get a negative unless you have complex numbers, but we're not dealing with complex numbers or imaginary numbers. So we are going to say, nope, once again, we have no issues here. So now what I'm going to do is I'm going to take these two values, okay? I'm going to take these two values and plug them into my original function. Now this is tedious work, right? Because you have to actually plug that into my original function here. I'll grab the whole thing. So I'm supposed to do those two values into here and get some answer, right? So again, I'm going to go to my calculator and do this quickly. How are y'all feeling while I'm typing this in? How is this feeling to you all?
Feeling good.
Not too bad.
Not too bad.
Go for it, seems good.
Okay.
Not too bad. Just seeing when he's gonna go from the extreme.
Yeah, I mean, it's tedious. I mean, that's really what this comes down to, is tedious, but you can't understate, or I can't understate the power of what we have in our hands now. This is a very, very powerful technique to find, the highest and lowest values of a function. So if you plug in negative 1.24 into that, you should get negative 0.404. If you plug in, what was that? Is that 3.24? Yeah, 3.24. You should get 0.154. Okay, that's step 1. Now I move on to step 2. Now I need to plug the endpoints into the function, which were -6 and 6. And so if you plug those in there, you should get negative 0.175. And if you plug in 6, you should get 0.125. All right. So here are the 4 outputs that we're looking at, and we're comparing them. We're trying to figure out which is the biggest and which is the smallest. Smallest meaning furthest to the left on the number line. So what's the biggest?
The negative, or sorry, the 1.54 or point
The
one.
0.154. This is our absolute maximum,
Max.
right? 0.154 is the biggest number we have. What's the smallest?
Negative 0.4.
Negative 0.404.
Yeah, this is our absolute minimum. So I gave you an example for this one where the endpoints, the maximums don't happen at the endpoints. And we can kind of see it from the picture. Let me go back to the graph, if you don't mind. And let me just change one thing on the graph, might make it a little easier. Let's change this to a 1, and let's change this to a -1. Yeah, I think that that helps illustrate what we just found. So here's the graph again, from -6 to +6. And we can see, it looks like right around here. Where is that? Oh, at 3.24, right? About 3.24. We got a value of about 0.154. There it is. That's the global maximum. And right here, this is happening at -1.236, spits out -0.404. What do y'all think?
Not too bad.
Yeah, I mean, think about it in the big picture, in the big picture of things. Had I walked into class today and I asked you, hey, everyone, take a look at this function, but only look between -6 and 6, and go tell me, I mean, even if I showed you the graph, okay, even if I showed you this graph, I'm going to go a little bit further. Let me go 0.4 here, -0.4 here. What if I showed you, I said, hey, everyone, you know, here's the picture for you, even like here it is. Can you tell me where the global max and min are? Right? That would be difficult, right? That seems difficult, doesn't it? To actually figure out where that point is occurring and where that point is occurring. Like that seems like a hard question. But what we're learning today is that we can do it so long as we can take the derivative, set it equal to 0 and solve it, and then also look at where the derivative doesn't exist. If we can do those things, then we'll be able to find these highest and lowest points.
And
All
sir,
right.
quick question.
I'm sorry?
I have a quick question.
Yeah.
The notes you're writing down on that like notepad thing, we can see it from the canvas, right?
These?
Yeah.
I will post these. I haven't posted them in a while, but I'll just go back and post all these. I don't think I have. No one's asked for them. So, you know, they're on the YouTube video, but I'll post them as notes.
Okay, thank you.
Now, the things that I write on the screen, like this blue thing, that's a different program I'm using, and it doesn't archive this. It's archived on the video, but it's not going to be in the notes.
Okay, I understand.
Okay. Okay. Yeah, this is a big freaking deal today. All right. Let's try another one. It's time for us to get more serious now. All right. So same instructions. F of x equals x times the square root of, let's go with 9 minus x squared. And let's look at that on the interval -1 to 3. All right, so I'm going to go refill my drink. What I'd like you to do just right now, real quick, take the derivative. Okay, just go on the side, use some scratch work, take the derivative, because we're going to need it, right? So when everyone taking the derivative, I'll be back and we'll go through the steps.
I want to refill my drink too.
I'm going to start writing the derivative down so you can look at it. Who has questions on the raw derivative? Anyone? Are you sure? Okay. Now, up to this point in this class, I've been happy with that as an answer, but we know we're going to have to set that equal to 0, right? So let's get to that. Let's get to that in a moment. All right. So I'm going to go through the steps. First thing, this is a, okay, continuous function. Is this a continuous function? Well, we actually have some problems because you can possibly plug in a value of x here and get the square root of a negative number. For example, what if x was 5? Right? What would happen? You get 9 minus 25, and then you get a negative under a root, and that wouldn't be good, right? So the domain of this thing is not anything. The biggest number we could put here is 3. Because if we put 3 here, 3 squared is 9, 9 minus 9 is 0. We can take the square root of 0. We just can't let it get bigger than 3. Do you all agree with that?
Yes.
Okay, so look at our domain. It's between -1 and 3. That should be okay. Because even if I plug in -1, -1 squared is +1. Take away 9, or 9 take away 1, we have 8. So that I can do. So this is continuous, right? It is continuous on this interval. So we can proceed with the closed interval method. Had this interval gone from like, you know, -10 to 10, then we couldn't do it. All right. All right. So the first thing I want to do is I want to find the critical numbers. So I want to figure out where's the derivative 0. And I want to figure out where the derivative does not exist. So we go and we take the derivative, right? So I take my derivative, and when we took our derivative, here's what we got. We got square root of 9 minus x squared minus x squared over the square root of 9 minus x squared. So all I did here was I canceled the 2's. This 2 and this 2 go away. I still have a negative, which is why this is a minus now. And then this x and this x multiplied together become an x squared, and I just slid it on top of this square root. We good there? Okay, I eventually have to set this equal to 0, right? That's what I eventually have to do. So I want to get to that property a over b equals 0, where I can just look at when a is 0. And I'm thinking that because I have a fraction. So to get to the point where I have a fraction equal to 0, I have to put those two together. So I have to actually look at this as a fraction and get a common denominator. Oh, I forgot to put the prime, everyone. Sorry, prime. Do y'all see that right there? I forgot to put prime. So what do I have to introduce? What do I have to multiply the top and bottom of this by to get the same denominators?
Square root of 9 minus x squared.
Yep, I have to do that on top and bottom. Square root of 9 minus x squared on top, square root of 9 minus x squared on the bottom. That's what I'm multiplying that first fraction by. And then on the other fraction, I don't need to do anything to it because it already has the square root of 9 minus x squared. So now when I put those together, I multiply those two together. What happens when I multiply those two together?
They become 9 minus x squared.
Yeah, the roots just go away, right? 9 minus x squared.
Sorry for whoever I just cut off.
No, you're
Yeah.
good.
And then you have the minus x squared from the other numerator. And then all of that over the common denominator, square root of 9 minus x squared. Right, because they both have the same denominator. So all we do is we just put whatever this becomes minus that, we put that on top, that's all of this. And then the denominator is just common. And I'll go one more step. This is 9 minus 2x squared over square root of 9 minus x squared. And there is a pretty nice clean version of the derivative, right? This is like a clean, simplified derivative instead of the raw one, right?
We just stopped there, like,
No, we're not stopping.
That's
That's the clean derivative. We still need to set
Oh,
it to
okay.
0, right?
okay then,
So it
yeah,
sets
let's
to
just
0.
like,
So here we go. I'm going to do the setting of 0 over here so I have some more room. So f prime equals 0 means, so now I'm finding the critical numbers. I set 9 minus 2x squared over the square root of 9 minus x squared equal to 0. But see, now I have a fraction equal to 0, right? I had to put these together. I had to put them together first before I could say I have a fraction equals 0. So this means all I have to do is set the numerator equal to 0. And that's quadratic, but it's easier to solve than a normal quadratic equation because I'm missing an x term. I can just do some basic algebra, move the 2x squared to the other side to make it positive. I can divide both sides by 2. And then I can get on my calculator and take the square root on both sides. And I have to do plus or minus. So I'm going to get on my calculator and I'm going to do 9 divided by 2, right? Which is 4.5. And then you take the square root of that. So you should get plus or minus 2.12 is x. I have two answers. Two critical numbers. Questions?
okay. Yeah, so then you said, because it's a fraction, you set the numerator to 0. I should not try and take the derivative of it again, doing like quotient rule again and again,
Well, not yet.
right?
Not yet. That's coming
Oh.
in the next section. It's not happening
Oh.
today.
Okay then.
Yeah,
So for right now,
unfortunately,
just stop.
yeah, unfortunately, everyone, what's coming later is that we'll have to look at the second derivative also. But that's coming later. So we'll have to take
Love it.
derivative of that again, quotient rule, and then we'll have to set that to 0. So the algebra is just going to start to get really, really
Intricate?
punishing.
Yeah.
I think
Oh,
punishing is
okay.
the word.
Okay then. That's a
So
word.
we need to look at where the derivative doesn't exist now. Okay, so let's go back. Here's our derivative. Is there anywhere where we could have problems here? Well, yeah, I mean, we could get division by 0, couldn't we?
Yes.
And what about square root of a negative number? That could happen also, but we already know from the original problem that between -1 and 3, we're never going to get a negative under here. So that we're okay with. But what about at 3? What if I try and plug 3 in here? Wouldn't I get 9 minus 9? And then
Yes.
give me division by 0? So I actually do have a critical number here. X equals 3 is a critical number because that is a point that would make the derivative not exist. It would make the derivative undefined if I tried to plug 3 in.
Oh, okay. We don't look at it and try and. I'm sorry. I think I keep trying to solve it and like to finish it all up. I'm sorry. Never mind.
Okay. All right, so now what do we do with these? We have three critical numbers. What do we do with them? We take them and we plug them into
The equation, the original.
original function, right? Okay, so I'm going to plug in positive 2.12, negative 2.12, and 3 into the original function. And again, to save us time, I'm not going to go through all that. I'm just going to get it here on my calculator. 9 minus x squared. Hurry up. Okay, so when I plug in 2.12, I get about, it's about 4.49999. I'm going to say it's about 4.5. When I plug in negative 2.12, I get negative 4.5. And when I plug in 3, I get 0.
Sorry.
We're done with step 1. Step 2 is I need to do the endpoints, right? And the endpoints were a -1 and 3. So it just so happens that our endpoint is also a critical number here. But so we don't have to do the math twice. We know it's 0. But we do have to plug in -1. And at -1, I get negative 2.83 or something like that. So here they are. I don't need to look at 0 twice. Absolute max, 4.5. Absolute min, negative 4.5. Where do they happen? At 2.12 and negative 2.12. All right, y'all ready to look at the graph of this? See what it looks like? So here it is. X times the square root of 9 minus x squared. And we're looking between -1 and 3. 3? Yeah, 3. And I need to change this back to something reasonable here. How about -10 to 10? Okay, there it is. There's the graph of that function. Wait, hold on a second. Did I mess something up there?
Yeah, I think f of -1, I got -3.16.
Did I type this in right? Hold on. X times. Oh, I know what's wrong. Oh gosh. Okay. Good. I made a mistake. Awesome. What did I do wrong? Does anyone see it? Where okay, look at the absolute minimum. And this is exactly what I just warned you about a second ago. The absolute minimum is -4.5, right? That's what I said. Where does that occur? -2.12. Where's -2.12?
Yeah, that's outside of our range.
It's not
Yeah,
in here.
not
Not in
yeah.
here. So I was supposed to throw that away and I didn't. Okay, I'm gonna get punished in math purgatory for that. Okay, so that means I'm gonna throw this answer out because it's not within our interval. Does everyone understand that? That is not in -1 to 3. So we're not considering it. And that means our real absolute minimum would have been this one. It happens at -1. Now, this is the correct answer. Whoever said that they got something different, this is correct. Okay, that makes me happier now. Let's go back and look at the graph. Here's the picture. Hopefully you see there's our global minimum, and then here's our global max. And to figure out where they are, if I hover over it, this global max happens at 2.12, that's what we said. And the answer is 4.5. And then the global minimum happens at, it's not showing it. Well, there we go, -1, and you get -2.83-ish. Okay. All right, now there's more problems that I can do here because there's a lot more algebra that you need to see, so how weird the algebra gets here. But I could do a ton of problems, and then, you know, you'll get a new problem on your homework and you'll be like, I don't know how to do that. So you have to go through your homework. Definitely go through your homework, watch my videos to help you if you get stuck on the algebra. I think what I'd like to do now is just kind of give you a weird problem to kind of see how we might be able to use this. The problem's not going to seem useful at all, but it's just, I think it'll be kind of interesting that we'll be able to solve this. So I want us to find two numbers whose sum is 30, but whose product is a maximum. Right, so I'm giving you your first word problem related to this section, and it's a weird problem. And again, it doesn't seem like this is very useful, but it gets us starting to think about how we're going to set up word problems. So I want us to find two numbers whose sum is 30, but whose product is a maximum. So what do I mean by that? I mean, give me two numbers that add up to be 30, first of all. So give me two numbers that add up to be 30.
15 and 15.
15.
Okay, 15 and 15. So 15 and 15 are two numbers that add up to be 30. Agreed? So they add to be 30, right? And I want their product to be the biggest it can be. So what's 15 times 15?
215.
What is it?
215.
215, okay? So this is that's one set that someone told me, two numbers that add up to be 30, and when you multiply them, you get 215. Somebody give me two different numbers.
12 and 18.
225.
Wait, what? Sorry?
15 times 15 is 225.
I thought it was 225, okay. Didn't want to argue. Two other numbers.
25 and 5.
25 and 5. Okay, do those add up to be 30? Yes, right? What do they multiply to be? 125, right? Which was bigger? Which gave us a bigger product? This one, right?
Yeah.
All right. But there's a lot of other numbers I can try, right? I mean, I can try a lot of different numbers, can't I? Like, I don't know, I could do 10 and 20, right? 10 and 20. Those two numbers add up to be 30. But when I multiply them, I get 200, right? Which is still smaller than that one, right? So it looks like maybe 15 and 15 seem to be the best numbers that add up to be 30 and give us a maximum product. Do y'all see what I mean by this? Like this product right here appears to be the maximum, but the question is it? Are we sure there's no two other numbers that add up to be 30 and give us maybe a bigger product? Do I understand the problem?
Yes.
Okay, so watch how I'm going to formulate this. Do you all agree that X and Y can represent the two numbers that we're going to pick? Yes?
Yes.
Okay, and do you agree that X plus Y must be 30 in order for this to work? Yes?
Yeah.
Do you also agree that the product, I'll call it P, is X times Y?
Yes.
Yes? Do you also agree that I can rewrite the product if I take, if x plus y must be 30, do you agree I could rewrite this as y equals 30 minus x? So I could solve this for y, right? So if the product must be x times y, but y must be 30 minus x, then I can rewrite this as x times y, but y is 30 minus x. And that means the product is 30x minus x squared. Are y'all following me?
Yes.
Yes, yes. I would like to know when you have the absolute maximum of this, what's the absolute maximum that this can be? Right? That's the question that I'm asking you. What's the absolute maximum that product can be? So now you ask yourself, is P a function? Is it a continuous function? Is that a continuous function? It's a polynomial, right? It's a
Yeah.
polynomial. Is it on a
Yes.
closed interval? This is a key question. Is it on a closed interval? Is X restricted between two numbers?
No.
You sure?
Well,
It can be.
It says
has
fun-
30.
I mean, it can't be greater than 30.
Yeah, so I didn't say this, but let's assume that these have to be positive numbers, okay? Just to make our
Okay.
lives easier here. These have to be
well, it
positive.
says find
Oh,
two
it can't be
numbers.
less than 0 and it can't be greater than 30.
Yeah, if we say that these have to be positive, then the smallest x would be 0, right? Because if x is 0, y would have to be 30. Do you agree with that? For them to add up to 30? So the smallest x would be 0, then y would have to be 30. Or you could have x go all the way up to 30, which would mean that y would have to be 0. Does that make sense? So we have a restriction on what x could be. And now we're basically doing a problem that we've just learned how to do today. So I've got a continuous function on a closed interval. And so the first thing I'm going to do is I'm going to figure out where's the derivative 0. And I'm going to figure out where the derivative does not exist. So the derivative of this is a very quick derivative, 30 minus 2x. If I take that derivative and I set it equal to 0, I get 30 minus 2x equals 0. Move the 2x over, divide by 2, I get 15. Interesting. That's a critical number. I then ask myself, when does the derivative not exist? Does not exist. When does that happen? Well, the derivative is nice, right? 30 minus 2x, that's a nice function. It's never going to have a problem. So I only have one critical number. So now what I do is I take that 15 and I plug it into the P function. Now I didn't call this P of X, and maybe I should have, but I'm going to plug 15 in for the product function, and I'm going to plug it in right here. So it'll be 30 times 15 minus 15 squared. And I believe if you do that, you should get 225. Yeah. You get 225. I also have to check the endpoints. So this is step 2. What is the product at 0 and what is the product at 30? So if I plug 0 into that product function, I get 0. And if I plug 30 in here, I'm not going to do it, but if you do it, you'll get 0 also. So that means that your absolute maximum is 225. So I'm not expecting you to be like completely on board with me with what happened here. What I want you to understand is this. The problem that we were posed with to find two numbers, and I should add two positive numbers, just to be clear here. To ask you to find two positive numbers who add up to be 30, but whose product is a maximum, you could sit here all day long coming up with different examples, okay? And one of you could sit here and argue, well, I think it's 15, 15. And someone else could say, no, there might be some other numbers. Y'all can sit here and debate all day long. The math is the truth, okay? The math shows us that 15, x being 15, which means that y would have to be 15, is the maximum product you're ever going to get. That makes sense? Like there's no arguing about it anymore. And a lot of times in the real world, you'll have situations where a person, a human being, will sit there and look at it and be like, no, it's got to be this. And then when you do the math, you realize that no, you're wrong, okay? Those things are referred to as being counterintuitive. We cannot always trust our brains and our minds and our intuition to be correct. We have to have something to fall back on. And the method here of calculus is the truth, I guess. Okay, I still have 14 minutes. I want to do another example.
Hey, Professor, can we do an example with ln?
You want something with natural log?
Yes.
Yeah. Okay, how about this one? How about if we take the function f of x equals the natural log of x squared plus 3x plus 4. Let me graph it first because I want to make sure that it's going to work the way I want it to. Natural log of x squared plus 3x plus 4. Let me give it a bigger interval here. Yeah, there we go, -4 to 3, that'll work. On the interval -4 to 3. Same instructions. I'm going to start moving a little faster. Okay. So is this a continuous function on this interval? That's a little hard. That question's actually kind of hard, but you could plug a -4 in here and you'd see that you're okay. You're going to get a positive number here if you plug -4 in. If you plug 3 in, you're going to get a positive number here, so you can do the natural log. So everything in between should be good. Now, let's start doing the derivative because we're going to need it, right? So the derivative of this, the derivative of natural log of something is 1 over it. Times the derivative of what's inside 2x plus 3. You'll agree?
Yes.
Okay, now let's move the 2x plus 3 on top. And that's a pretty clean version of the derivative. Now I'm going to figure out where it's 0. So if I figure out where it's 0, all I have to do is really set the top to 0. Do y'all agree?
Yep.
And if I solve that, I get -3/2. Take the 3 to the other side, divide by 2. This derivative doesn't exist. Well, that would mean that we'd have to look at x squared plus 3x plus 4 being 0, right? Can't be 0. But you can check again for yourself. Like this has no, if you try and do this like quadratic formula, you'll get negatives under the roots. You'll get a negative under the root, which means there's no solution to this. If you try the quadratic formula, which means that we have no problems here. You understand this can't be 0 because then you have division by 0, right?
Yep.
So we have to just check quadratic formula, you get no solution. Was there a question? No?
I was just agreeing.
Okay, good. All right, so there we go. We're going to plug these in. Now, what we're going to wind up doing is we're going to wind up plugging in this answer. I'm going to do it over here on the side. We're going to have to plug the -3/2 in here. And then we're also going to have to plug in the endpoint. So I'm just going to kind of do it all at one time here. We're going to compare all these. And this, I think you'll need a calculator for. You'll have to plug in this into the natural log. Okay, here we go. When I plug in 3/2, which is the same as 1.5, I'm sorry, negative 1.5. I get 0.5596. By the way, I didn't ask this and I almost screwed it up again. Is this point in here?
Yes.
Yes. Is this point, well, those are the endpoints. I don't need to check those. Okay. So I get that. What if I plug in -4? -4, I get 2.08. If I plug in 3, I get 3.09. So this will be our max. And this will be our min. Here was the graph. And you can see that we have a negative 1.5. We have a minimum value of 0.56. And then our max occurs at this endpoint right here. At 3, we get 3.091. Okay, go ahead.
Will you ever mix like ln and then problems like these together?
I mean, there's a plethora of situations you can run into. Let's do one more.
But will
try-
an ln cut off the e since they're kind of same?
What? ln and e.
Yeah.
I didn't say e. Did someone say e?
I don't know. I heard Brian saying e.
What'd you
Or
say,
was-
Brian? No?
I just asked.
I'm sorry. It was me then.
Okay. Yeah, I mean, you could have a function that has e and ln in it, but they would only cancel if it was e raised to the ln or if it was ln of e. But you could have e to the x times natural log of x. Like, don't do this. We're not going to do this. Okay. Like we
Sorry.
could look at that. We could look at that, but I don't want to because I'm a little afraid that we won't be able to solve the equation. All right, we have to be real careful. I have to be able to give you problems that you can solve the equations. Like you may not be able to solve the equation if I just make up a problem off the top of my head. So I have to follow some format here or else you start having issues. How about this one? 4x minus tangent x. And let me graph it so I can give you a good interval. 4x minus tangent x. And let's go from, let's go negative pi over 3. No, negative pi over 2. Well, I'm trying to come up with a good interval here. There we go. Negative pi over 4 to pi over 2. All right, this is your first example with the trig function in it, right? First example. All right, so here we go. Let's just, because I only have 6 minutes, let's just get down to the nitty gritty here. Let's take the derivative of this, which should just be 4 minus secant squared x. Right? Now what we need to do is figure out where is this derivative. You know what? Hold on. Let me think about this. Can I change the problem to make it easier for us so we don't need our calculator? Let me change that 4 to a 2. It'll make our lives a little easier. Let's figure out where this derivative is 0. That means we need to set 2 minus secant. Oh, you know what? Hold on. I forgot there's a square there. Take it back to 4. Shit. I think I'm ready for the weekend. 4. Take it back to 4. I apologize. Okay, so we want to do 4 secant squared x equals 0. Okay. Now, this is the first time we've had a function, a trig function that we have to solve for x, but we all took pre-cal. We all passed pre-cal. And so one of the things you want to do in pre-cal is be able to solve a trigonometric equation. So I moved the secant squared to the other side to make it positive.
It would be -4, wouldn't it?
I left the 4 on the left. I moved the negative secant squared to the right.
Oh, okay.
So now I'm going to take the square root on both sides, plus or minus square root of 4 equals secant x. That kills off the squared on the secant. Plus or minus the square root of 4 is same as plus or minus 2. So what this means is that secant x has to be 2 or secant x has to be -2. You all agree with that? Now, secant x by definition is 1 over cosine of x. That must be 2, or 1 over cosine x must be equal to -2. And so if I flip this side over, the left side, if I flip the fraction and make it cosine x, then I have to flip the fraction on the right, which is 2 over 1, and that becomes a half. Same thing on the right one, cosine x equals -1/2. So I guess what I'm saying is to say when is secant x 2 is the same as asking when is cosine x 1/2. And if we say when is secant x -2, it's the same as saying when is cosine x equal -1/2. Now, this is where you really need to know pre-cal. Cosine x equals a half means at what angle on the unit circle is your x coordinate 1/2? Can somebody tell me?
2 pi over 3.
Isn't it?
Right?
I didn't hear what you said.
Oh, I said 2 pi over 3.
It's 60 degrees,
no.
right?
60 degrees. It's right
60
here
degrees. My bad.
because your x
Said
coordinate there
negative.
is 1/2, right? Now, okay, 2 pi over 3 is correct for the other one, but hold on, we're not done
Oh,
here.
okay.
That's the x coordinates 1/2. And then this also happens down here at, so what angle is that? So this angle right here is pi over 3. And this angle all the way over here is what, 5 pi, sorry, 5 pi over 3. There are 2 places where it happens, pi over 3 and 5 pi over 3. So that means my solutions here so far are x is equal to pi over 3. And or x could be 5 pi over 3. I'm going to throw away the 5 pi over 3. Why?
Outside of
It's
our.
not within our interval.
It's not within our interval.
Our
Our
range.
interval only goes from -pi over 4 to pi over 2. So really, we're only allowed to be looking right now between here and there. That's all we're allowed. We're not allowed to look anywhere over here at all. Actually, anywhere over here. We have to look between -pi over 4 and pi over 2 straight up. So we can only be looking at angles that live in here. So pi over 3 is an answer. Now, what about this over here? This is saying where on the unit circle is your x coordinate -1/2? And that's what Danielle was saying, here and here. But I'm not even gonna look at those. Why? Again, I can only look
Not within
between
the-
here and here. So I'm only allowed to be looking at answers in here. So I don't even care. I don't even care about that at all. So I only have one critical number, pi over 3. So now what I do, and I'm out of time, is I need to go to the original function. I need to plug in pi over 3. That's my critical number. I need to plug in the two endpoints, negative pi over 4 and pi over 2. And then I need to plug those into the function and get some answers. And I'm out of time. I can't do it, but we'll look at the picture. This right here. Oh, wow. It even showed it. Look at that. At pi over 3. Look at that. At pi over 3, we have a max. And then over at the other endpoint over here, this was at this is negative pi over 4. But that's not going to be our minimum. Our minimum is actually, whoa, holy shit. Where is the minimum? There it is. It's way down here somewhere. You'll have to mess with that one. Okay. So we're done. Your homework for this weekend is to get started on your homework for 4.1. It's a very important section. All right. Hopefully by going through the homework, you're going to start to see the amount of different sort of algebraic methods and techniques you're going to have to employ. And you're going to get a little lost and a little confused and a little discouraged, but just keep grinding away at it, okay? Get with me if you need help, all right?
For sure.
Okay. Do your homework though. Don't skip it.
Yes, I'm gonna do it.
Okay.
Thank you.
Have a great weekend, everyone.
Thank you. Have a good weekend.
Yeah.
Yep.
Bye.
Mhm.